This exercise is an extension in a way of the previous exercise where we had extracted building footprints. This time we are going a step further and extracting the roof forms. So the first step involves basically loading and exploring the dataset. There are two folders, one pertaining to the 3D base map and the second one containing the building related dataset, LiDAR dataset that is. So once we open the 3D base map on ArcGIS Pro, we will add that particular folder containing the LiDAR data as a folder connection in the software so as to enable us to access the particular LiDAR dataset. The 3D base map's role is that it contains all the steps to extract roof forms which has been pre-created by Esri team so that we do not have to remember each and every individual steps by ourselves. So this is just a documented workflow which exists in that particular folder. So as a first step, what we have to do is to create a LAS or a laser dataset. Now again, those who have seen the previous video on building footprint would know that this particular step entails merging the various LiDAR files available in our dataset into a single LiDAR file, because this is a step which is necessary to do the post-processing. In the create LAS dataset, what we will do is basically select the 4 LiDAR datasets. Thereafter, we shall name the dataset because it is over the Portland, Oregon area in USA. We'll name the output merged LAS dataset as likewise, and then we will ask the tool to basically create a LiDAR point cloud for us. The point cloud has been created. It's a vivid mix of various colors. You can see that the high elevation values are in yellow and red and orange respectively, whereas the low elevation values are in blue, dark blue respectively. It is in feet. The measurement is in feet and not in meters. This is something which you must be aware of. So 236 feet is the tallest spot and the 70 feet, minus 70 feet is the bottom spot in the particular LiDAR dataset. This data has been acquired using airborne LiDAR, as in via an aircraft or via a drone. There are a sum total of 1 crore 40 lakh data points in this LiDAR dataset. So you can understand it is a very, very high resolution, detailed, comprehensive dataset, which is why LiDAR is used in the first place, because it enables us to get very good length, breadth and height XYZ measurements. This is where we'll do something different from the building footprint exercise. What we'll do is we'll extract the elevation values, but of 3 different types. One is the default digital elevation model, which captures the height of the features on the ground. But beyond that, we will also extract the digital surface model, which captures not only the height of the ground level features, but then also artificial or natural features above the ground level, such as vegetation or buildings or any other features respectively. And the third dataset, elevation dataset, would be the normalized digital surface model, which is capturing the relative difference, you can say, between the DSM and the DEM. So it is essentially the relative height of features above the ground level. So 3 different data sets have been created. The layers have been created on your left. Each of them captures the elevation values. Let's switch on the LiDAR point cloud layer once again. We'll do some corrective actions now, because you see that the bottommost point is at the height of minus 70 feet. So obviously there is certain discrepancy or error in the LiDAR calculations. Even the topmost point will, just verify by clicking on the various features in the dataset to understand whether is it a true representation or not. Subsequently, what we will do is the elevation surface values which we had extracted, we'll put a minimum and maximum height feature parameter within that. So what we are saying is that you do not categorize points which are below 0 feet, and you do not categorize points which are above 15 feet, because 215 feet is above the tallest building in the vicinity. So that much of detailing in the data is more than sufficient. We do not need any elevation values which are over and above that, whereas the minimum of 0 feet is self-explanatory, because below 0 feet, the underground features are as it is not captured by the LiDAR software. What we will do as a next step is to load the building footprint layer onto the map view. This particular layer is readily available for us as part of this project package. We had created this layer from scratch from the LiDAR point cloud in our previous Caselet video on building footprint. You may refer to it in case you wish to. The attributes of this particular layer are quite detailed, right from the address to the description, to the type, to the usage, to the elevation values. A whole variety of data is included as part of this layer. Typically, municipal corporations maintain such layers with as much as details they desire. And I believe the source of this particular layer file is also from a similar entity. Subsequently, what we shall do is to change the elevation surface into a more precise version of it. By default, the global elevation layer is good for macro level visualization, but then to have a neighborhood level precision, we are better served to convert the file elevation from the default global elevation to the digital elevation model, which we had as part of the which we had created as part of the project package. It is positionally also very accurate, spatially accurate, and directionally accurate. Subsequently, you would have noticed that the values of elevation are mentioned in feet. This is to demonstrate that using a raster calculator, we can convert these values into any particular dimension which we choose to capture. In this case, we will convert it into meters, units of measurement. So how do we go about doing it? Is multiplying the feet values by 0.3, which would give us the values in meters. Once we load the formula in the raster calculator tool, the computation is done and the new layer has been created. Subsequently, we will reproject the digital terrain model. Reprojection is a technical concept for those who are not familiar with it. To put it simply, we are changing the coordinate system of the layer in question. In this case, the digital terrain model, which we had created in meters. We do so as to maintain consistency between this layer and the other layer, because in the subsequent processing steps, multiple layers will be used together for doing certain precise computation. And if the layers do not have a standard projection, then it basically leads to errors in computation. What we will do as a next step is to have this reprojected digital elevation model as part of the elevation surface. So if you remember, what we had done previously was to include the digital terrain model in place of the global elevation default in ArcGIS. This time we are even making it much more accurate by including the reprojected digital elevation model as part of the surface elevation. We can do a few more steps, such as publishing what we have created so far in this exercise onto the web for sharing it with public and other stakeholders. But for this particular exercise, we will not do that. To distinguish a particular roof form from another is a challenging task which requires a high level of precision. So as a first step, what we will do is to run the segment roof parts tool. What essentially it does is take the current 2D building footprint, which is a very basic representation comprising of simple shapes, into a much more complex representation which mimics reality. we use the digital surface model to add a moderate level of spectral and spatial detailing to the footprint layer. Once the result comes out, you will see that it now comprises of very many complex shapes and patterns. A sum total of 1039 unique shapes have been created once we have run this tool. Initially, the building footprint had only 940 such shapes. So, a fine layer enhancement of detailing has been added in this new layer. Now that we have the 2D building footprint, which is realistic in nature, we will use that as well as the 3 elevation surfaces which we had created at the beginning of the exercise: the digital surface model, the digital elevation model, and the normalized elevation model, to basically create the 3D building footprint, which forms a basis for us to create and isolate and distinguish the roof forms. So using the create buildings tool, we will now move on to creating the accurate 3D building footprint. Once the tool runs, we will be able to use the symbology to basically depict it on the map view, because currently, as you would know, that the map view is 2D in nature, but the new layer which we've created is 3-dimensional in nature. So we need to configure the symbology so as to allow the software to depict the newly generated 3D building footprint layer in a nice 3-dimensional form. The symbology rule packages have been added. They have been part of our project package file in advance. We didn't have to create it separately. And once we've done this, the building footprints are now visible on your screen. It is still currently displaying in the 2-dimensional form, but as we navigate the scene in 3D, the building footprint layer is clearly visible in its 3-dimensional form. Let's explore the attribute table. Because this is a 3D layer, a shape area field also has been computed. But more importantly, what is also computed is the type of the roof form. 3 varieties of roof forms have been captured. One is hip, flat, and gable. These are standard North American type of roof forms available over there. Upon examining the statistics, we are seeing that the flat roof form is the most common, followed by gable, and then followed by hip. Now, is this the end of the processing? Not clear, not quite, because we need to check the accuracy and repair any errors in the building footprints which have been generated. So, when we review the buildings, we begin by using the confidence measurement tool. This tool allows us to compute the root mean squared error, the RMSE, for the building elevation values. Essentially, the 3D footprints' elevation values are compared to the digital surface model which we had generated earlier, and any inconsistencies are measured and displayed as the RMSE, which you are going to see in a moment's time. We see when we sort the RMSE in descending order that there are roughly 800 plus building footprints which have a root mean squared error of above 3 feet. 3 feet is a kind of a benchmark for us. We would like our building footprints to have a error of less than 3 feet. If we select a particular row from the attribute table, automatically ArcGIS highlights that building footprint. Subsequently, what we will do is to visualize this particular layer based on the RMSE values. As we load that particular step, it is important for me to convey that the tasks section which you see on the left of your screen is a predetermined created workflow which we've downloaded from the ArcGIS solutions page. There are nearly 125 plus such workflows out there for any person who is willing to explore, let's say, an avenue in emergency management, in say capital project planning, in fire hydrant inspection, and a variety of other workflows. You can go and explore that for yourself on ArcGIS solutions page. As a next step, as I've said, we will visualize the building footprints as per the RMSE. What we've done is loaded the symbology file, which has certain commands and instructions on how to basically visualize the same. So we do not have to manually set the parameters, but essentially what we've done is we've categorized the footprints using different color combinations. So a footprint with a green outline is having a favorable RMSE, whereas a footprint with a red outline has a highly unfavorable RMSE. So subsequent to this categorization, we will initially begin working by repairing or fixing the building footprints which have the highest RMSE. Often we toggle between the views of 3D and 2D because certain workflows are much more suitable, less cumbersome to be done on 3D, and sometimes it is applicable the same way for a 2D application. Sometimes it is even better to have both the 3D view and the 2D view stacked side by side so as to get a 3D perspective of the area under observation as well as see a depiction in 2D as well for better understanding, which is exactly what we have done over here. We'll switch on the LiDAR point cloud. The area under highest elevation is containing the root mean squared error. So we will see why is that particularly the case. It has an elevation value of 230 meters. And the RMSE value is 28 feet, which is much above the 3 feet, which is desirable for us, and hence it is marked in the red color. It is often important to save the ArcGIS project at regular intervals so as to enable us to have the latest project package in place just in case malfunction happens and the application has inadvertently it shuts down or the PC turns off and so on and so forth. Next, we will proceed to show a live demonstration of how to basically correct a particular error. What you are seeing on your screen on the right is that the underlying imagery is from a different perspective, as in it has been captured from a different angle, and the building outlines do not fall directly above the imagery. So to visualize it better, we also have an option in ArcGIS Pro to download historical imagery. So we've downloaded the imagery from 31st May 2017 as it is captured from a particular angle which would directly complement the building footprints angle which has been captured from. You see now the underlying building footprint is closely resembling the base map. What we will do is correct the shape over here, because the elevation value right at the middle, where there appears some sort of exhaust fans over there. So the shape which was detected was slightly distorted, as in it was away from it. So we use a manual tool to edit the vertices so as to place it directly on top of the particular cross section of the building roof. Now, what is the benefit of this? You see straight away the line is now colored yellow, because now it corresponds to the surface elevation model much more closely, as in the root mean square error is much lesser. So initially it was orange, but then after we've manually edited the vertices to closely resemble the roof's exhaust section, we have basically reduced the RMSE, and the footprint is now much more accurate. With this, we come to the conclusion of this video caselet. The roof forms which we've extracted from the LiDAR imagery can be used in subsequent workflows such as urban planning and zoning, as well as more technical workflows such as solar and shade analysis, which is useful for residential and commercial rooftop solar planning purposes.